This session we will be covering about oxidative phosphorylation, which will be costing about 8 marks in university examination. Actually, it's a bit a lengthy topic, so I selected this topic to make in 2 videos. In this video, we are going to cover about what is the introduction to oxidative phosphorylation and the concept of oxidation and the enzymes involved in oxidative phosphorylation. So let's get into the topic. The introduction to oxidative phosphorylation. Actually, we do so many works in day-to-day life. For doing these works, we require sufficient amount of energy. The primary source of this energy is nothing but the food we take. The food we take may be a carbohydrate or a protein or fat. All these are nothing but hydrocarbons. The hydrogen part of hydrocarbon is accepted by coenzymes like NAD and FAD. Now these coenzymes are called as reduced coenzymes as they accepted the hydrogen atom. Now these reduced coenzymes are going to mitochondrial respiratory chain where they are oxidized, where the hydrogen atom is passed from one complex to other complex, releasing sufficient amount of energy. This energy is captured and it is useful for phosphorylation of ADP into ATP. Now this oxidation coupled with phosphorylation is our topic known as oxidative phosphorylation. So friends, let's once summarize up what I have told. It is we require food to get energy. The food may be a carbohydrate, protein or fat, whatever may be. These are hydrocarbons. The carbon part is oxidized to CO2 where the hydrogen part is accepted by NAD and FAD, and they are now called as reduced coenzymes, and they are now sent into the mitochondrial respiratory chain, and where they are passed from one complex to other complex, releasing energy. This energy may not be useful for us at that point of time, so this need to be stored, and this is stored in the form of phosphate, that is ADP conversion into ATP. Now here comes the question, what are high energy phosphates and low energy phosphates? So we have to define these both. The high energy phosphates are defined as the compounds which are going to release more than 6 kilocalorie per mole by the hydrolysis of their phosphate group is known as the high energy phosphates. Repeat with me. It is the compounds which are going to release more than 6 kilocalorie per mole on hydrolysis of their phosphate group. Whereas the compounds which are going to give less than 6 kilocalorie per mole are termed as low energy phosphates. Now comes the question. Give some examples of high energy phosphates and give some example of low energy phosphates. The examples of low energy phosphates include those which are utilizing ATP. Take the pathway glycolysis where you are going to see glucose 6-phosphate is utilizing the ATP. So one of the example is glucose 6-phosphate and other one is a fructose 6-phosphate and other one is a glucose 1-phosphate. These are going to utilize the ATP. Then high energy phosphates are those which are going to release ATP. Take example carbamyl phosphate or phosphoenol pyruvate, which is going to release ATP. And next is a 1,3 BPGA. It is also going to release ATP in the glycolysis pathway. So friends, the first topic, subtopic introduction to oxidative phosphorylation is being completed. It is we require food to give us energy. The food may be carbohydrate, protein or fat, whatever it may be, they all are hydrocarbons. The carbon part is oxidized into CO2 while the hydrogen part is accepted by coenzymes like NAD and FAD. Now these are known as a reduced coenzymes. These reduced coenzymes are going into the mitochondria where they are passed from one complex to other complex, releasing sufficient amount of energy. Now this energy need to be stored in the form of phosphorylated, and this oxidation coupled with phosphorylation is our topic, oxidative phosphorylation. Here comes the question defining of high energy phosphates and low energy phosphates. Those compounds which are going to liberate more than 6 kilocalorie per mole on a hydrolysis, they are going to call as a high energy phosphates, and the examples are those which are giving ATP. They are 1,3 BPGA, carbamyl phosphate and phosphoenol pyruvate. And less than 6 kilocalorie per mole, you are going to see they are less energy phosphate. Examples are which are receiving the ATP. Those include glucose 6-phosphate, fructose 6-phosphate and glucose 1-phosphate. So the next topic is concept of oxidation. Okay friends, let's discuss about oxidation. What is actually the oxidation? Oxidation is nothing but losing of electrons. Say example that Fe2 plus is losing one electron to gain positivity Fe3 plus. It is an example of an oxidation reaction. Now the electron lost, maybe it may be lost in other form like hydrogen. If you consider hydrogen atom is consisting of one electron and one proton. It means removal of an hydrogen atom indicates removal of an electron. You are going to see AH2 plus NAD plus. Now what happens? NADH plus H plus. You are going to see AH2 is oxidized in this reaction. The question may be like that. There is no loss of electrons directly you could see, but there is a loss of electrons in the form of hydrogen atoms which are accepted by the coenzymes. Now this type of reactions are known as the oxidation reactions. Now you are going to see each and every particle is going to exist in two states. One is a reduced form and the other is a oxidized form. Both are going to constitute and known as a redox couple. Tell me friends, what is redox couple? It is the reduced and oxidized form of an atom is known as a redox couple. Each and every redox couple is going to have one redox potential. This redox potential is measured in laboratories. Redox potential is nothing but the tendency to accept the electrons. The tendency to accept electrons. The one which is having more redox potential is having the more tendency to accept the electrons. If you are going to see a respiratory chain where it is consisting of 4 complexes, there is a passage of one electron from one complex to other complex. By their redox potential values, they are going to increase. You are going to see the last complex which is having the high tendency to get electron, that is having high redox potential, whereas the first complex is having less redox potential and less tendency to give an electron. So friends, let's get into the next topic. It is what are the enzymes involved in oxidative phosphorylation. There are 4 classes of enzymes that are involved. The first class is oxidases. The second class is dehydrogenases. The third class is hydroperoxidases. The fourth class is oxygenases. Tell along with me friends. It is the first class is oxidases. The second class is dehydrogenases. The third class is hydroperoxidases. The fourth class is oxygenases. So let's discuss about all these enzymes. The first class of enzyme, oxidases. It is going to remove hydrogen particles from the substrate and it is going to pass it to the oxygen molecule. Take example that AH2 plus O2. In this reaction, the oxidases are this hydrogen particle and they are going to give these hydrogen particles to the oxygen molecule. Remember, this reaction may also occur like this. So friends, what are the reaction catalyzed by the oxidases? Oxidases are going to remove the hydrogen particle from the substrate and they are going to pass this hydrogen particle into the O2 molecule. If you are going to see, you are going to get H2O2 or H2O. It is dependent on the prosthetic group that is present. If the prosthetic group is flavoproteins, you are going to get H2O2. If the prosthetic group is metalloenzymes like copper, you are going to get water. So friends, what is the function of oxidases? It is the function of oxidases is releasing of hydrogen particle from substrate to the oxygen molecule so that the hydrogen peroxide or water is going to form. It is dependent upon the prosthetic group that is present. If the prosthetic group is flavoprotein, you are going to get peroxide. If the prosthetic group is water, you are going to get metalloenzyme. Sorry, I am a little bit confused. If the prosthetic group is a metalloenzyme, you are going to get water. The next class of enzymes, dehydrogenases. In dehydrogenases, you are going to see hydrogen particles are removed from one substrate and they are carried to another substrate. In oxidases, they are carried to the oxygen molecule, whereas in dehydrogenases, you are going to see carrying of hydrogen particle from one substrate to other substrate. You are going to see example that AH2 is converted into a carrier protein, that is a prosthetic group. It may be an NAD or FAD or porphyrin, something. Whatever may be the carrier protein, they are going to remove the hydrogen particle from the substrate and they are going to pass to another substrate. You are going to see in this example, the AH2 is the main substrate. The hydrogen particles are removed by the carrier protein, that may be NAD, FAD or porphyrin, and this is sent to the other substrate, that is a B, which is converted into BH2. So the next class of enzymes is hydroperoxidases. In hydroperoxidases, you are going to see it is consisting of two classes of enzyme. One is a catalysis and another is a peroxidases. The catalysis is going to convert H2O2 into H2O plus O2. You must remember this much is enough. And the last class and the most important of all these enzymes is the oxygenases. Oxygenases are also known as multifunctional enzymes. What is the function of oxygenases? They are going to incorporate the oxygen molecules into the substrate. See, if you're gonna see the first reaction, that is A plus O2 gives rise to AO2, you are going to see two atoms, that is two oxygen atoms are going to incorporate into the substrate. These type of enzymes are known as dioxygenases. In the second example, you are going to see only one oxygen atom is included into the substrate. These type of examples are known as monoxygenases. You have to know about the monoxygenases because they are also known as multifunctional enzymes or hydroxylases. Let's see about monoxygenases. Monooxygenases, also called as hydroxylases, are classified into two groups. One is a mitochondrial hydroxylase system, other is a microsomal hydroxylase system. Mitochondrial hydroxylase system is present in an inner mitochondrial membrane, while microsomal hydroxylase system is present in microsome. Microsome is nothing but the membrane of endoplasmic reticulum. Now the question may be asked like this: what are the components of microsomal hydroxylase system and what are the components of mitochondrial hydroxylase system? So you have to know what are those components. The microsomal hydroxylase system is consisting of cytochrome P450, NADPH, and cytochrome P450 NADPH reductase enzyme and molecular oxygen. So friends, remember the microsomal hydroxylase system, which is useful for catabolism of xenobiotics, that is metabolism of xenobiotics, which is going to make insoluble xenobiotic into soluble xenobiotic so that it may be easily excreted. So the first, what are the components of microsomal hydroxylase system? It is consisting of cytochrome P450 NADPH and cytochrome P450 NADPH reductase and molecular O2. And the mitochondrial hydroxylase system components are cytochrome P450, iron sulfur containing protein adrenodoxin, the iron sulfur protein which is also known as adrenodoxin, cytochrome P450 adrenodoxin reductase. Instead of NADPH, we are going to see here adrenodoxin. So you are also getting cytochrome P450 adrenodoxin reductase and molecular O2. Thank you friends for watching this video, and next video will be posted in a short soon. Thank you.